There we go. We record these. The director, Dr. Platchan, Peter Platchan, is the director of our observatory, and we are blessed with 4 graduate TAs to help us organize not only just the various observing projects that we have on campus with our students and also with the research, but also for public outreach. M. Funny Pong, who will be giving the talk next week, is seated here. We also have Patrick, Kevin, and Mohammed are our other 3 graduate TAs. In addition to that, we have a number of tour guides. Emmy and Andrew are both both of those. And in addition, we are blessed with having a very active student organization called Friends of the Observatory. This is led by Jonathan Saldana. He is going to be also on the roof, and he will be the primary point person with the telescope, so he will tell you all about the telescopes and what they're pointing at. If you are a student here and you're interested in astronomy and interested in actually using our telescope, feel free to join the organization. They have events almost every couple of weeks at this point, and they often use our solar telescope during the day or the 32-inch telescope by themselves or for themselves at certain events. So if you're interested in astronomy and you really want to have more of a hands-on experience, like I said, I highly recommend joining that. Our observatory is currently expanding. Specifically, we are expanding our outreach opportunities. One of the things that I am hoping to do with our program is to take our telescopes and our inflatable planetarium out to the various counties, Prince William, Loudoun, Arlington, and so forth, to schools or places that do not have the resources that would ordinarily be able to have access to telescopes or planetariums. And that unfortunately does take money to do. And so if you are interested in becoming a patron of the observatory and helping us out financially, that would be great. This is my least favorite part of the talk. There are various levels that you can participate at, and like I said, these fundings, this money will go to helping us support not only the regular operations of the observatory, such as public nights, such as this one, but also, as I said, for more of a mobile outreach to the community at large. If you're interested in the observatory and learning about the observatory, what we do here, what the students are doing here, I again highly recommend that you subscribe to our online newsletter, The Moon, the Mason Observatory Outreach newsletter. In it, we feature students of we highlight students of the month. Someone here is going to be our student of the month. We talk about constellations, or we talk about space news, what's going on. I will be writing a next newsletter. I will be either writing about DART, the mission that tried to deflect an asteroid, or I will be talking about Artemis. So that sort of thing. Now, I think I've rambled on long enough, so I will introduce, it's my pleasure to introduce Dr. Eve Lee from McGill University. She will be giving a talk, Planets Big and Small. At McGill University, she leads a astrophysics group specializing in the formation of stars and planets. She got her PhD from UC Berkeley and was the recipient of the Annie Jump Cannon 2022 award from the American Astronomical Society. Annie Jump Cannon was an instrumental woman astronomer, a woman in astronomer, or astronomer who's a woman, back in the early 1900s when they referred to them as computers. So it's a very high honor, and I congratulate you on that. And now I will turn it over to you.
All right, thanks, Dr. Parks. Let me just share my screen. Just want to make sure that the slides are showing up correctly.
So far, so good.
And that everyone can hear me? Okay, great. Thank you again, Rob or Dr. Parks, for the nice introduction and also for the invitation. It is my pleasure to join you all, albeit remotely. I'm still to share with you some of the research that I do at McGill regards to the exoplanets and the physics of planet formation. So until about 30 to 40 years ago, the only known planetary systems in our galaxy was our own, the solar system. And it was not until 1988 when we had the very first detection of an exoplanet. You may not have heard about this, and that's because it was such a controversial detection at the time. And by the way, it was made by Canadian astronomers, and being Canadians, they were very polite about it and didn't really make a big news out of it. And the reason why it was so controversial is because detection of an exoplanet is a really difficult endeavor. Because we're trying to find the signal of something that is about 100 times smaller than the star that it orbits around, and also about 1,000,000 times lighter than the star that it orbits around. So it's still really hard. Imagine how difficult it must have been all the way back in the 80s. In fact, for this particular detection, it was not until the early 2000s that people have went back to verify that indeed this really was a bona fide exoplanet. And what won the Nobel Prize in Physics in 2019 was the first detection of an exoplanet around a sun-like star. And that is a very important qualifier because it drives at this, one of the major motivations for exoplanet science. Are we living on a planet in the planetary system that is a special place in our galaxy? Is the solar system rare, or is it a dime a dozen? And of course, you can't really answer that question with just a single data point. And in fact, this particular exoplanet was a really weird one. It looks nothing like what we see in our solar system. So to really get at this question of whether we live in a special place in our galaxy or not, we launched what is called the Kepler Space Telescope, launched by NASA in 2009. And it is this mission that really revolutionized this field by finding thousands and thousands and thousands of other worlds out there. So right now we have a little more than 5,000 detected and confirmed exoplanets, mostly thanks to Kepler, but also some ongoing missions right now. And it's not just the fact that it found so many exoplanets, but it's the fact that most of these exoplanets look nothing like what we see in our solar system. For instance, our solar system is very much ordered. We have these small planets on the inside, from Mercury to Mars, mostly a rocky body. And the large giants on the outside, from Jupiter to Neptune, the gas giants and the ice giants. But these other worlds out there, some of those are really weird, like this hot Jupiters. So this was what won the Nobel Prize in Physics, and that we found a bit more. So it's a Jupiter, it's a giant, it's a planet that's as large and as massive as our own gas giant Jupiter, but really, really, really close into its host star, about 4 times closer than how Mercury is to our own sun. But turns out this is a very rare kind of planet. Only about 1% of sun-like stars have these planets. And for most of the planets and planetary systems that we have detected, they're still weird in that they're very compact. So often we find about 3 to 5 or sometimes even more planets all packed into this inner region within about the orbit of Mercury. And furthermore, most of these planets have the size that lies between that of the Earth and Neptune. So we call them super Earths and mini Neptunes. Why? Because we just do not have any solar system analog. We have no such planet in our solar system. So in that sense, our solar system is rather weird. But we need to be careful about that statement, because if we take a look at this from what scientists would like to look at, so this is measured masses versus orbital period. It's a plot. of all the detected and confirmed exoplanets in circles. And to give you some comparison, I plotted in diamonds the solar system planets. So the reason why I said you need to be careful about statements like our solar system is rather weird is because notice how we have all this blank region. At the moment, we don't have the technological capability to really detect a true solar system analog. So we can't quite say definitively that our solar system is very rare, but we can still say that our solar system is still a bit weird in the sense that we don't have any of the short period planets, and we don't have any planets that lie between that of the Earth and Neptune, which really abound in our galaxy. About 60% of all sun-like stars have these kind of planets as short orbital periods. And just to give you some idea of how exactly astronomers go about and detect these planets, I've color-coded these with respect to the 4 major detection methods. So the blue is transit. This is what Kepler has used. It's also what the current transit mission TESS is using right now up in the sky as we speak. So this is monitoring the brightness of a star, and if the star has a planet, and if that planet happens to cross our line of sight, blackening out certain parts of the star, then we're going to see a little dip in the brightness. The frequency of this dip, like how often we see this dip happening, tells us the orbital period of this planet. And the degree of this dip tells us the relative size of this planet with respect to the host star. The black points are the radial velocity, and this is what was used to detect those like first detection of exoplanets. And this looks at the spectra of the stellar atmosphere, and we search for its blue shift and the red shift. It uses the Doppler effect. The same thing when you're out on the roadside and there's a car coming, zooming by. As it zooms towards you, you hear like a higher pitched noise, and as it goes away from you, you hear less and less high pitched noise. Same thing, but with the light, we see blue shift and the red shift that comes about due to the motion of the star, or we call it the wobble of the star due to the gravity of the planet. At a more technical point, the star is moving around the center of mass that got shifted due to the gravity of the planet. The red points over here, those are directly imaged planets. Here is one example. This is an actual scientific image. You see 4 dots over here. That's actual planet. This is emission coming from the planets themselves. So these have to be massive and young planets so that they're still bright, and they also have to be far away from the star so that we can actually resolve their signal. And finally, the yellow points over here, those are micro-lensing planets. And this uses the gravitational lensing effects. In other words, the deflection of the path of the light due to the gravity of certain object. So there's some background source light that is coming that's coming towards us, but then it gets deflected due to the gravity of some foreground star. And let's say the star is being orbited by a planet. That planet has some mass, so it's also going to act as a secondary lens, deflecting yet again that light, and it causes a little bit of a deviation in terms of the degree of magnification or the brightness of the light source coming from some background object. And due to the ways in which the stars are organized in our galaxy, this particular method is sensitive to the planets that are at around a few astronomical units. In other words, the Earth-Sun distance. So those are the different detection methods. And now I'd like to draw your attention to the fact of just how diverse these exoplanets are, this population. At any given orbital period, I have a huge ranges in terms of the masses. I have something as massive as giants and something as small as the Earth, or even smaller. How exactly is it that our galaxy and the nature came up with this huge diversity in the population of planets. And the shape of this population is more easily seen when you take a look at the measured size of the planets rather than the masses. And that's just because it's much easier to detect the sizes rather than masses. So here is a histogram of the planet sizes going from left to right. It's small to big, and small planets are mostly rocky. Whereas the large planets, these puffy planets, have to have some massive and thick gaseous envelope on top. And you'll notice right away that it is quite broad, but in our galaxy, we have much fewer larger planets as compared to the smaller planets. So let me first introduce you to some of the terminologies, or rather, it's like exoplanet taxonomy that we give to label different kinds of exoplanets. So the really small ones are, of course, rocky planets. These planets, these are still rocky planets, but we call them the super Earths because they are blown up version of the Earth. It's like very large rock, mostly rock. And there's a little bit of a dip and it goes back up. This is the famous peak of mini Neptunes. It's a scaled down version of a Neptune, so it must have some gaseous envelope on top. And just to give you some idea of what kind of thickness and what kind of weight of an envelope we're talking about, this mini Neptunes must have about 1% by weight gas envelope. Comparing that to the Earth, it has an atmosphere, it keeps us alive, but it's a really, really tiny amount of atmosphere, only about 1 part per million. So in the grand scheme of things, our Earth has a really, really thin amount of an atmosphere. And going beyond the size of a Neptune, we have much, much fewer giant planets. The number dwindles by about a factor of 10, if not more. So our galaxy prefers the formation of the small planets, the mini Neptune, super Earths, and rocky planets, as compared to the gas giants like our own Jupiter. So why is that the case? This goes to the heart of the question of how exactly do planets form? And planet formation begins from the formation of stars. Until very recently, I used to show the images coming from the Hubble Space Telescope, but we now have the JWST, the Webb Space Telescope, up in the sky, operating very well, giving us this first images in exquisite detail of this astronomical objects out there. So here is one part of Orion Nebula. It is a nearby star-forming region. You'll see this bar-like structure. It is a dense region of gas and dust where stars form. And if you can zoom into those regions, you'll see like all these filaments. And if you can zoom in inside those filaments, you will see clumps of gas and dust, which will eventually collapse and form the stars. But as it's collapsing, it's also spinning. And whenever you try to, maybe you've done some clay work, if you've ever tried to squish something that is spinning really rapidly, you might recall it's really hard to squish it in a certain direction, and you end up with a pancake. And we call it a disk. In fact, JWST is so amazing that we actually have an image of this young disk around young stars that is still enveloped by a cocoon of gas and dust right over here. Let me zoom in. Here's the disk, here's a cocoon. And just to impress upon you the degrees of this big ranges of size scale that we're talking about, that is an orbit of Neptune. Fits right within the disk. And just look at how much we had to zoom in to get a sense of what kind of size scale we're talking about when it comes to planetary systems. Neptune is the farthest out planet in our solar system. So this is a spinning disk of gas and dust, and it is inside the spinning disk of gas and dust that we have the formation of planets. And we call these disks as protoplanetary disk. Let's zoom in inside this protoplanetary disk and talk about how planets assemble. If I were to describe to you a planet in its very simple term, I would say it's a rock with some gas on top. That's what our Earth is. So where does that rock come from? It is a solid rock, so it has to come from some solids within this disk. And I said that this is a spinning disk of gas and dust. And when I say dust, I'm talking about like a micron-sized dust grains. And what is a micron? You get a micron when you take a strand of your hair, depending on your hair type, but typically, if you're able to cut it along its length by about 100 times, 100 to 200 times, you get about a micron. So the point is that it is really, really, really tiny. You have to somehow go from this really, really, really tiny micron-sized dust grains all the way to a few thousand kilometer-sized rock that we're all sitting on right now. How does that happen? Well, there's still a lot of missing pieces of puzzle that the entire community is still trying to figure out. And I'll briefly go over that in a bit. But for now, let's just assume that it has happened because we see it. It must have happened. And this rock is massive enough that it can gravitationally attract and hold on to some gas from this disk and form the planetary atmospheres. But while that is going on, the disk gas itself is also evolving. In fact, on the outside, the gas gets blown away by the wind generated by the high energy photons. So think like X-ray, UV rays that generates the winds to blow off the gas on the outskirts of the disk. On the inside, the disk gas gets drained onto the star, or it gets funneled onto the star. We know this because we can directly observe them in the spectra of these young stellar objects. So what does this mean for planet formation? This means that there is some time limit because there is a finite lifetime for this disk, especially if you want to create a planet with some gas envelope on top. That must all happen while the disk gas is still around, well within the lifetime of the disk itself. And we'll see how this plays out when we talk about the creation of the diversity of different planet population. So let's talk about the different sizes of the planets and therefore creating planets with a different gas mass content. Again, we're going to start with the rock that has already formed. It is massive enough. It is massive enough to have some gravitational sphere of influence. And inside this gravitational sphere of influence, you will be able to attract and bind some gas and form the planetary atmosphere or planetary envelope. And during that gravitational attraction process, that actually heats up this envelope. So you're dealing with a pretty hot gas that is sitting in a colder environment. And whenever you have some hot material sitting in a colder environment, that hot material will eventually cool off. It's just like when you have some hot tea or hot coffee in a mug and like you're sitting out in the open, especially right now, we're on the East Coast, so it's getting a bit colder. I'm not sure if it's cold there as Montreal right now, but anyways, it's relatively cold. So your hot drink will cool off over time. So same thing happens here, except we're dealing with gas. So when you have a hot ball of gas that is cooling off, it tends to shrink. So that might be hard to really picture because we're more in everyday life, we're more used to liquid rather than gas. And liquid, and this is more apparent for the gas material. But if you have easy access to liquid nitrogen, you can make a cool demo out of this by just using a balloon and some beaker full of liquid nitrogen. I did not have easy access to liquid nitrogen, unfortunately, because I'm a theorist. And but I managed to get this from YouTube. It's publicly available of people making demo and showing this demo. And I think I forgot to share audio, so I don't think the audio will show up. But if it doesn't, then I'll just explain along.
This is a beaker full of a little bit of liquid nitrogen.
Sorry, can I just check with the people if you could hear the audio?
We can hear the audio.
Okay, great.
I have a helium balloon here, and it's not floating because it doesn't have much helium in it, and the weight of the balloon is pulling it down. I'm also going to fill a balloon with my own breath. And then I'm going to dip the balloon in the liquid nitrogen and ask what happens to it. Shrinking. Why? Because it's cooling the air in the interior of the balloon. And in fact, kind of crackling and becoming
All right, so as you have seen, that balloon, when it was placed in the beaker full of liquid nitrogen, it was cooling down. So all that air within the balloon was cooling down, and therefore it was shrinking. And if you have noticed, like, what happens to the balloon when he pulls it out of the beaker, it actually try to go back to its original shape because the room temperature was actually higher than the air within the balloon. So that actually started to heat up the air in the balloon, so it expands back. All right, going back to the exoplanet. So this gas, this hot ball of gas, it cools down and therefore it shrinks. That means you have all this empty room within the gravitational sphere of influence to cause a refill. So you have all this gas that's trying to refill this gravitational sphere of influence. That means this planet is building more and more thicker and more weighty gas content. So based on this simple thermal physics, we can write down an equation that to identify some key ingredients that really drive what should be the final gas mass content for each given planet. So I have identified the 3 key ingredients here. The first one is more obvious. The more time you have to build this gaseous envelope, of course, this envelope is going to be more thicker. So this relates to when exactly this rocky cores assemble with respect to how much time is still left until the disk gas all disappears. And the second ingredient might not be so obvious, this Z that the astronomers call it metallicity. It really goes to, it's really talking about the degree of pollution. So the less polluted your envelope is, the easier for that envelope to cool. We see this in our own planet atmosphere. It's basically inverse of the greenhouse effect. When we have too much polluters in our atmosphere, that acts as some blanketing. It's a blanketing effect. And it's much harder for that atmosphere to transport away the energy, and it starts to heat up. So it's the opposite of this, where you have less of an envelope, the envelope is more transparent, and it's easier for that envelope to cool down and therefore accelerate the growth process. And the most important ingredient is the mass of this rocky core. So the more massive it is, the stronger the gravity, and it's easier for this planet to rapidly build more massive envelope. So let's first focus on these 2 factors, how massive the cores are and how much time this core had to build this gaseous envelope, and see how this bears on creating this diversity of exoplanets that we observe. And again, this goes back to the original question of why is it that our galaxy prefers the small planets over the large planets? This is the expected planets for different mass of the core and also the different times at which the cores have assembled. So going from bottom to top, we're looking at thicker and thicker atmosphere. Going from left to right, we're looking at heavier and heavier rocky core. the colors here correspond to when exactly these cores have assembled. So yellows are the cores that have assembled really early, and it had a full disk lifetime to build their gaseous envelope. Whereas for the purples, these are the cores that have assembled so late that it barely had any time to build their gaseous envelopes. So we can make one-to-one comparison between what we see here to what kind of planets we expect to observe should we observe these planets. So over here, we're dealing with planets with really thin atmospheres. So we're talking about the rocky planets like the super Earths. Here we have intermediate size of a planet. So we're dealing with mini Neptunes. And all the way up here, we're dealing with the giants, the gas giants like our own Jupiter. And this is a theoretical model. And of course, any good theorists need to be able to compare their expectation to the observation. So here is a direct comparison with the data, at least for those where it's where the data is available. And we see a general good agreement, except for this red points, which are known special planets called the super puffs, and they just require a special formation channel. But the point here is to realize that even in our expectation, it's just really hard to create this massive planets because they, first of all, need massive cores, and those cores have to form really early. It's much more likely for us to have this larger ranges of intermediate size and more rocky planets. And furthermore, on top of this, the very fact that we just see so many of the small planets as compared to the large planets means that it's a natural process. It just likes to create the planetary cores. It just takes a while to assemble. So can we try to unpack that a bit? Why is it that we expect this planetary cores to take a while to assemble? And here I'd like to go over briefly this assembly process of this rocky cores. Again, we're starting from this really tiny amount of really tiny dust grains, about a micron-sized dust grains. And I'll go this a step by step. And the first step is going to be a huge one because we're going to go from a micron size to about 1 to 1,000 kilometers. Part of it is that this is the part where we have the least amount of understanding. But in general, we do think that it's a combination of the electrostatic forces. It's the exact same force that creates the dust bunnies in your room if you haven't cleaned it in a while. And on top of that, there's also aerodynamic drag. That means all this dust grains, the solid grains, feel the drag due to its interaction with the surrounding gas. And all those together is expected to create this 1 to 1,000 kilometer size object. So starting from here, we have a better understanding of what kind of physics is at play. So from 1,000 kilometers to something like Mars-sized. Here, electrostatic forces is no longer effective, but rather we're talking about aerodynamic drag plus gravity. So the idea here is that you have some 1,000 kilometer size object, and you have all this like smaller particles that's streaming by. And those smaller particles feel the gravity of those 1,000 kilometer size object, plus it feels the drag of the gas. And that allows this tiny grains to fall onto this 1,000 kilometer size rock. And that is a continuous process that causes a further and further growth of this 1,000 kilometer size rock to something larger like Mars, for example. And how do we go from Mars-sized object to something larger, like the Earth, or something like few times the Earth, like most of the exoplanets that we can detect right now? So on top of aerodynamic drag and gravity, we also need to consider the collisional mergers, because the process that I just talked about, this combination of aerodynamic drag and gravity, that eventually shuts off. So if you'd like to grow to even larger sizes, you need to have 2 of those rocks and have them collide and smoosh to create even bigger object. So you can call it collisional merger, or if you're a planetary scientist, we also call it the giant impact. So for the creation of this massive few Earth mass planets that we typically observe, that final assembly process is governed by this collisional merger or giant impact processes. And that giant impact is really hard to happen when there's so much gas around at the beginning of the disk evolution. Because what happens there is the disk is so full of the gas, and you have all the small rocks that are orbiting around the star without ever really crossing each other. Because it's really hard for those rocks to be deflected from its own motion. It's the exact same thing as if you've ever tried to run across a swimming pool, not swimming, but just running across. You might recall that it's really hard to do that as compared to just running in open air. And that's because all that dense fluid that is hindering your movement, it's really hard for you to deflect from your initial path. So same thing with these rocks. You need to wait until the disk gas is just about to disappear for these rocks to deviate from its path, thanks to the perturbation, the gravitational perturbation from its neighboring rocks, for them to collide and merge to create even bigger objects. So you can actually do the calculations to figure out just how much the gas has to disappear. You have to deplete the gas by about 1,000 to 10,000 times. So it's really dramatic. So you really have to wait until the very end of the disk lifetime. So this explains why is it that we often see the more smaller planets as compared to the large planets in our galaxy. But it's not like the gas giant doesn't exist at all. We see them. We have two of them in our own solar system, the Jupiter and Saturn, which I think I just heard that you will get to observe them today. So then how do we create them then? So if we want to create the gas giant, we again have to start with the massive core, and we have to accelerate the gas growth process as much as possible. Turns out there are special locations within the protoplanetary disk that can really promote this massive growth of planets in a way that we can bypass this collision and merger process and just achieve this using the combination of the aerodynamic drag and gravity. In fact, in the measurements of the gas giants, the gas giant population, there is evidence of a preferred location. This is a histogram. We call it occurrence rate, just the number of gas giants per 100 stars. As a function of the semi-major axis, that means how far these planets are from the central star. And we see that there is a definite peak between 1 AU and 10 AU. Again, that's AU, astronomical units, so Earth-Sun distance. Our own giants fit this picture. There's Jupiter, there's Saturn, so it falls within this peak. So what's so special about this 1 to 10 AU? Why is it that there's this intermediate, some sort of a sweet spot of where we expect the emergence of these gas giants? So let's first talk about this from the assembly process of the cores. We need to create massive cores. And using that interaction between the interplay between the gravity and the aerodynamic drag, that process will just shut off when the core has reached certain size. Because when you're dealing with something that is so heavy, it tends to perturb the surrounding area. It perturbs the surrounding area so much that it carves out a gap and it shuts off any further inflow of the material from the outer region. In fact, we see this directly in the radio images of the protoplanetary disk. This is an actual scientific image of a protoplanetary disk looking at the dust emission. Notice right away that there's a deficit over here. There's a gap. And it could be due to these planets. And because the disk tends to be thinner closer to the star, it's really easy to perturb that really thin part of the disk. So it doesn't take much to perturb that inner region. In fact, you can do this with just about something about the size of the Earth. But as you go farther and farther away, the disk gets thicker and thicker and thicker. So it's really hard to perturb that thick material. You need to grow to even larger and larger sizes. So just looking at this, it sounds like, well, like we can just keep going farther and farther away from the star, and we should be able to create these massive cores. But the reality is a bit more complicated, and that's because if you go too far away from the star, all the clock starts to run much more slowly. In other words, it takes a long time for these rocks to clear out its own orbit so far away from the star. So it's going to take a while for this course to grow to its final size. So that naturally creates some intermediate region within the disk where you have this optimal location for the formation of this massive cores. Now, just having the core is not enough. You also have to think about whether you can really accelerate the gas accretion process. And here we're going to go back to the effect of the pollution. So less polluted the gas, faster cooling, and therefore more gas growth. And when it comes to the disk, there's a very special location where you expect this degree of pollution to change. And that is what is called the ice line. Why is it called the ice line? This is the location within the disk beyond which the disk is so cold. You're so far away from the star. The disk is really cold. So cold that all these dust grains will be coated with the solid ice. Think about like water ice. But on the inside, the disk is hot enough because you're closer to the star. There's a lot of radiation from the star, heating from the star, that all that ice layer gets sublimated away, gets evaporated, sublimated away. So that means you have smaller grains on the inside and larger grains on the outside. And the size of the grains are very important when it comes to the motion of the grains with respect to the surrounding gas. It's just like when you look at the river flow, and in that river, there are some different size of the solid material, like tiny little pebbles versus really, really fine sand grains. That tiny pebbles will tend to just move on its own a bit differently from the river flow itself. But those really fine sand grains, it's really easy for the sand grains to completely mix up with the river flow. And it's just going to stay with that water, that river flow. So something very similar happens here as well. So for these large grains, it's harder for the grains to be entrained with the gas flow. So they tend to move on its own, feel that drag, and they tend to drift in more quickly. As compared to the smaller grains, they're more entrained with the gas, much easier for them to be mixed up so that they just stay with that gas in this region. So the upshot is that on the outside, you're dealing with more pristine gas, but on the inside, the gas tends to be more muddy with all this tiny little dust grains. So combining all this together, indeed, we do find this sweet spot of the formation of the gas giants is exactly around 1 to 10 AU, because it turns out that is about the location of this ice line, which is exactly coincident with the observed peak in the giant population in terms of how far away they are from their host stars. All right, so that was an overview of how we can understand the formation of the planets from the context of driving this diversity, this diverse range of planets that we observe in the exoplanetary data. But in astronomy, often the next frontier and the improvements in our understanding is made when there's a good synergy between this theoretical work with the observational data, and those observational data made possible by new and novel technologies. So what are some future and ongoing missions that can further help us understand this planet formation process, and just understand in general why we see certain patterns in exoplanetary data? So there's one mission that I'm super excited about, and that's called the Roman Space Telescope by NASA, to be launched mid-2020s. The reason why I'm so excited is that this mission is unique in its capability to detect really, really low mass objects all the way down to something smaller than the Earth in the orbital semi-major axis between about a few astronomical units. So that is made possible because this is a microlensing mission. And the reason why that is so exciting is because this is it is a very unique capability to probe the region where we just have no reach right now. And this is exactly the region that we need to probe to get a sense of, or to have a hope to really answer the question of, can we find a true solar system analog? And are we really living in a truly unique planetary system? And I've shown you that this interplay between the dust material and the gas material, the initial material that make up our planets, is really important in understanding the initial formation processes of these planets. And ALMA has been very, very instrumental in this effort. It is a radio telescope. It's a series of telescopes, actually, because it's an interferometry. And it helps us probe the dust content in these young disks. And we found all this really exciting images of all these gaps and rings that tells us something about whether that's coming from the planets or coming from something else. And finally, I've shown you like one image from the JWST that's up in the sky operating, already gave us some exquisite images. There's a huge focus right now in exoplanet science from JWST. That there's a lot of excitement because it gives us a very precise measurements of the chemical composition of the planet atmosphere. What exactly are these exoplanetary atmospheres made out of? And that is exciting from the formation perspective as well, because the hope is that we can somehow link that compositions of the planets, rather the planetary atmosphere, to the initial location, the origin location of these planets. And in that sense, I'm also excited about the European Space Agency's Ariel. Expected to launch in 2028. And the reason for that is Ariel is solely focused on exoplanet science, whereas the Webb is for all astronomy. And the reason why that hyper focus in exoplanet science is useful is because to really get a sense of this connection between chemical composition and formation, we need to have a uniform and large enough sample. And to really look at some patterns and trends, and that is where Ariel would complement the Webb and really tell us something, some exciting possible trends and patterns that we might find in this data. So that's it from me, and thank you.
Thank you very much. I think we have a few minutes for questions. I will take the host prerogative and ask the first one. Let's talk about aliens, I guess. When we talk about exoplanets, we always want. I always kind of like the idea of habitability. So I was just wondering about your own opinion, given that you are looking at the numbers of planets and as a function of their density or their composition, do you think we will find a lot of planets that are habitable, or no?
Yeah, good question. So I think we need to first come up with a true definition of habitability, because there's already a lot of definition. Like the simplest definition is like whether it has the right temperature to hold like liquid water. So if that is the definition, then yes, I mean, we already found a lot of planets that fall within that definition. But if the question is about like, can you really hold life on those planets, then you need to be more careful, because then like you really get to the fundamental question about what is life. And I don't think anybody really has an answer for that.
All right. Does anyone in the audience have a question for Dr. Lee? Yes.
So, you mentioned about the water ice informing the other activities. I wonder if we have an idea when the water molecules do this form in the formation, but they already seem to be emulated.
Dr. Lee, were you able to hear that, or would you like me to?
No, unfortunately not. Could you repeat?
So the question is, beyond the ice line, you were talking about ice-covered dust grains.
Mhm.
So the question was, when does the water actually arrive? Or rather, when is the water built? Are the water molecules in the solar system or the stellar nebulae, or do they get built within the formation process?
Yeah, that's a really great question. So the water itself actually comes from the very beginning. This star forming environment that I was talking about, this nebula, the water is already there. But the idea is that there's a lot of processing of that water from the nebular stage to this disk environment. So for example, it's not like the water doesn't exist in this inner region, the inner disk. It's just that water is in the vapor form. So it's just that depending on like what kind of region you're at with respect to the nearby star, is the water in a solid form or is the water in a vapor form? But if you're asking about the initial origin of the water itself, it comes like all the way from the very initial star forming environment.
Okay. Yes.
So gas giants, this may be elementary, but gas giants have a rocky core. So what percentage of Jupiter's mass is the core and what's the gas? I mean, I went to school a long time ago and I thought they were mostly gas.
So the question is, you have the giant planets, the Jovian planets. These are rocky cores with tremendous atmosphere. What is the ratio of the atmosphere to the rocky core?
Yeah, great question. So let me first preface by saying that our current view of the Jupiter is rapidly changing thanks to Juno. But the general idea that there is some sort of a rocky material on the inside and gas on top, it's still intact. It's just that the distinction between the rocky and the gassy part is very fuzzy right now, thanks to our updated understanding from Juno. But in terms of the mass budget, so the total mass is about 300 Earth masses. And we think that rocky material is about 10 Earth masses. So it's about 30 times more gas.
Yeah. So the question is, in exoplanet studies, are most of the stars sun-like or not?
Yeah, another great question. So Kepler, for example, had a singular goal of trying to detect an Earth-like planet around the sun-like star, which it didn't quite manage to do that. So therefore, it was very much targeted around the sun-like star. So our current exoplanetary data is very much biased, or rather, it's very much focused around sun-like stars. But right now, there is a lot of movement to try to go towards a more cooler stars. So you might have heard about M dwarfs. There are various reasons for that. The first reason, of course, it relates to the habitability, as Dr. Parks was mentioning. So because these cooler stars are less bright, the zone of the habitability shrinks. So it's much easier to detect those potentially habitable planets around this cooler stars. The second reason is that our galaxy is such a way that the galaxy has a lot more of these cooler stars than something like a sun-like stars. So that means you have a lot more chance to get more planet depictions around this more numerous stars. So there's a lot of focus right now to try to find and detect more planets around this cooler stars like M dwarfs.
Yes. So there's a jump in 2015 to 2016. So the question is there a reason for the jump between the number of detections in 2015 and the number of detections in 2016? I believe you showed that in one of your.
And let me just get rid of this so that I can see. Right. So that corresponds to, so the Kepler data set came in the different sort of, I'll call it bursts, or we call it like a public release. And because it's not just because it takes time to get all the signal, and you need to clean it up to really say that this is a planet. This is we actually confirm that it's a planet, and this planet has like certain size based on our understanding of the star. So there's a bit of a delay because it came with certain schedules for this public releases. So there's one jump over here, 2013, 2014, and another jump 2015 to 2016. So that's just a scheduled like release of the data. And at some point, the Kepler used to be proprietary. That means it was only available to a limited group of people. And then they realized that that's probably not a good idea for science. And then it became public afterwards. So that might have contributed to some of these jumps as well.
Thank you. That's right. Yes.
Have spoken a lot about the limited view that we have of the sky. Is there any number that we can find as far as like the percentage of the sky that we can see? And then when, as a follow-up to that, with the new missions coming down the road, how much more do we expect that to?
So the question is, given the basically the selection bias, the bias of the stars that we can see versus all of the stars that, or all the planets that potentially could exist. How many of what percentage, in your opinion, have we found with respect to having discovered, with respect to how many they actually are, and how is that going to increase given the new mission coming in?
Yeah, great question. So let me answer this. I think the question was specifically about the stars.
Planets, actually. Sorry.
Sorry. Okay, so planets. As you can see, there's a clear blank region over here. It's completely blank. But if you sort of like try to extrapolate, like from here, we may have a lot more of this even smaller planets than what we can observe right now. So we may find a lot more as we try to reach down to this like very low mass regions, especially at those far out distances. And that is another reason why I'm so excited about Roman, because it is the only mission that has the potential capability to really fill up this space. No other mission could do that.
Okay, thank you. Yes, in the back.
I'd love a better definition of the pollution of the template that takes place here.
So the question is a more precise definition of the pollution of the atmosphere, essentially the metallicity.
Right. So what is the more precise definition? So the metallicity is basically anything more massive than helium in terms of elemental budget. And you can do this by mass ratio. So it's basically the mass content of all these heavier elements divided by the mass content of the lighter elements, i.e. hydrogen and helium, mostly just hydrogen. You can also do this by number ratio as well, but theorists like me like to use the mass ratio, but like what people like to quote in their data, in their observation, tends to be the number ratio.
So just to sort of add on to it, one of the reasons why I love astronomy is because chemistry to an astronomer is real easy. There's hydrogen, there's helium, and then there are metals. Anything that's heavier than helium, that's a metal. And so if you have heavier than helium, you have a lot more electrons around it, and it's harder for that light from deep inside to get out without one of these electrons basically snapping it up. And so that basically keeps that's the pollution. All right. I think unless there are any other questions, we're going to thank Dr. Lee again and go on up to the telescope.
Thank you.
Thank you very much. That was a great talk. Yeah, so thank you for being here. And we're going to sign off from the.
All right. Okay, sounds good. Thanks for the invitation.
No problem. Thank you for coming.
Bye, good night.
Bye.